Welcome everybody to Systems Modeling, and today we are going to cover the Laplace transform. So our topic for today is the Laplace transform. The Laplace transforms are tools used for linear systems analysis and design. So that's all what a Laplace transform is. It's just a tool, just like you have the hammer, you have a screwdriver. Those are all tools. You can use it for different things. And in this course, we want to use the Laplace transform for analysis to analyze our dynamic systems. As with all tools, they are designed to make some jobs easier. So by definition, we have this equation, this lovely equation that defines what the Laplace transform is. So all it's saying is you take a function and you convert that function, a function of time, you convert this function into another function which is s, which is the s domain. So the way we do that, we integrate between 0 to infinity. We take our function and we multiply it with an exponential e to the minus st dt, whereby variable s is a complex variable. So s is equal to sigma plus j omega. So this one is just a complex variable. And next we are going to look at an example on how to use this Laplace equation. Now we are going to look at our first example, and let's say, for example, we have this function. It says that find the Laplace transform of the following function. So the first thing that we need to do is we need to write down our Laplace transform equation. So we know that the Laplace transform of our function is equal to, as given by f of s, which is equal to, we are integrating between 0 to infinity, inserting our function, multiplied by an exponential e to the st dt. And we take our Laplace operator operating on our function, which is, again, we integrate between 0 to infinity. Then we need to insert our function, which is e to the at multiplied by e to the minus st dt. Now note, here we have two exponentials. So we can just combine the exponents at the top because the exponentials are multiplied together. These two exponentials, just basic mathematics. So again, we integrate between 0 to infinity, and then we take minus s minus a, okay, times t dt. Note, we put our minus here because we had a positive a. So minus times minus gives you the positive. And we have minus times the s give you a minus s. Then from here, we need to use our calculus knowledge by noting that this part here is just a constant. Okay, you can view it as a constant apart from the t, because we are integrating with respect to t. So s minus a is just a constant. So we can use the u substitution, and I'm going to use the green. So let u is equal to minus s minus a times t. So if we differentiate this equation, so du dt is equal to minus s times minus a, and remember our t disappears, okay, because we are differentiating with respect to t. Then we are going to solve for dt, because we need the dt to be able to substitute that back in here. So dt is equal to minus 1 over s minus a times du. Now we have u, we have dt. So we can substitute what we have here back into this equation. So I'm going to rewrite that. So again, integrate between 0 to infinity. Now we have e to the u multiplied by 1 over, which is your dt, s minus a du. Note, we say that we are going to treat this is like a constant, and with all constants that are inside the integral, you can pull that outside. Let me rewrite that. So we have 1 over s minus a integrating between 0 to infinity, e to the u du. Now we are ready for evaluation. So the integral and the du need to disappear so that we can evaluate this. So this implies that, oh, I forgot the minus here, and the minus here as well. Let me just put that into the brackets. The minus there. Where else did I miss the minus? Okay, I think everything is fine. So we have minus 1 over s minus a e to the u. Sorry for that. It's between 0 to infinity. That's what we are evaluating. Now, let me just move this up to here so that I have enough space. So now we need to evaluate this equation. And evaluating between 0 to infinity, especially for exponential, is the easiest thing. Very, 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 very easy, because either you drive the exponential to 0 or you drive the exponential to 1. Now, let's look at this. We rewrite again, it's equal to 1 over s minus a multiplied. Now, if we are evaluating as t goes to infinity, so we are going to have e to the minus infinity minus e to the 0. Okay, so we are evaluating between very, very, very small minus infinity and 0. So this part, this is going to go to 0. Okay, and anything e to the 0 is 1, and this is going to be 1. This, by viewing this, it's like, look at this. Remember, e to the minus something is decaying. Okay, now as it decay, and this is over time, as time increases, this decay is going to be very, 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 very small, and this is where it goes to 0. okay, and e to the 0 is equal to 1, okay. So now this is equal to 1 over s minus a. So now we know the Laplace transform of, so the Laplace transform e to the at is equal to f of s, which is equal to 1 over s minus a. So we are going to keep that in the bag, okay. Now what happens, let's say a is equal to 0. If a is equal to 0, then you are going to have e to the 0 times t, which is equal to anything times 0 is 0, e to the 0. E to the 0 is equal to 1. So the Laplace transform of 1, which is a constant, is equal to 1 over s minus, we say a is equal to 0, which is 0, which is equal to 1 over s. So the Laplace transform of 1 is equal to 1 over s.